So verifying identities, in fact, that says functions there, that should say identities. What that looks like is that they're going to present you with an identity, which shows that one expression is exactly equal to another, to the point that if we were dealing with all of this, we could just make that substitution that it's equal to cosecant. So it's up to us to verify them. So what we're going to do is make these different substitutions, and starting this I typically start with the messier side that kind of has more options for plugging in. And what we're going to do is simplify and simplify until we can get to the other side, basically, the other side of the equation. But the key is that we need to show our work, have our details in there, because it's essentially a proof. It's not a formal proof of mathematics, but we're proving that it is possible to start here and end up here. Now, as we go through this process, we'll make substitutions with those identities that we talked about: reciprocal, quotient, and Pythagorean. And with these, it's all really about the process, and it's probably a different form of mathematics than you've been used to. Maybe you've done these before, and that's fantastic. These kind of stretch the brain in a different way, and that will kind of keep pausing with these and be like, okay, what can we do? And we just kind of have to think about all the things that we know, everything that's in our brain, and think about what can we plug in. So with this, will be a lot of work to show, and then it's just a matter of plugging in the correct things. With these, there's often more than one path to the correct solution. So with that, if you go a different route with these, that's completely fine. I'm just going to kind of show you the way that I think about them. All right. So with this first one, what we want to do is start with all of this and have it be shown that it's equal to cosecant. So typically where I start is I kind of look at what we're starting with. So I have sine and cosine, and then I have cotangent in there. So the first thing I'm going to do is get everything in terms of sine and cosine, especially when my final answer relates really closely with sine. So I could even make that note that really this is the same thing as I want to end up at 1 over sine. So I'm going to change cotangent to the sine and cosine form. So again, when you write these, make sure the variable doesn't disappear. It's important to have that value of x in our functions. Cotangent is cosine over sine. And I'm just going to multiply those together. So cosine's like cosine over 1. So I still have this sine x over here. Cosine times cosine is cosine squared over sine of x. All right, so now I have these two separate pieces, and what I want to do is add them together. So this is where that review of rational expressions comes in. I have the sine of x over 1 plus cosine squared over sine. So what I need to do is make a common denominator of sine. So I'm thinking about this least common denominator is sine of x. So with that, I need to multiply by sine of x over sine of x so that I can combine those two pieces together, especially seeing that we have these two separate terms here and we're ending with just a single term tells me that we really need to combine them together. So sine squared of x over sine of x plus cosine squared of x over sine of x. And now we can add them together. So we'll have sine squared plus cosine squared over that common denominator of sine of x. And seeing that sine squared plus cosine squared is making me think of the Pythagorean identity, which says that sine squared plus cosine squared is equal to 1. So I can make this substitution in that numerator of just 1 over sine of x. And then here I have that reciprocal identity that 1 over sine is the same thing as cosecant of x. So end up there, and that verifies the identity that we had. We were able to start up here with all of that, and then adjusting to only in sine and cosine, make it so that we can actually add those rational expressions together into a single rational expression and simplify down, and looking for that Pythagorean identity when we can. All right, let's look at this one. So I'm gonna grab this piece over here. And like, you could start on either side. I could start with cotangent squared of y. Just gonna get stuck really quick. It's better to start with the messier side of the equation. So I'm gonna start with over here, and I am gonna change everything to sine and cosine. So in the numerator, I have that cosecant squared, which is the same thing as 1 over sine squared. And then separate it, and in the denominator, 1 plus tangent squared is sine over cosine. So sine squared over cosine squared. All right, so this right here is a mixed number. And if it helps, we could do something like, it's the same thing as 1 over x squared over 1 plus x squared over y squared. If that helps to see it in that form, just make sure that you note that sine and cosine are different from each other, so we would use different variables. But if it's easier to think in those terms, you absolutely can write it that way. But the idea is that we want to clear out these mixed numbers, these fractions within a fraction. So what we do is we want to multiply everything by the least common denominator. So that least common denominator, well, I have this denominator of sine squared, I have this denominator of cosine squared. So my least common denominator will be a multiplication of those two values. So sine squared times cosine squared. So multiplying this through, it's like we're multiplying the numerator by that value and the denominator. So up here, multiplying by sine squared, cosine squared. And same thing down here. I'm going to write it in this form first, but then I'm going to adjust it so that we can more clearly see. But the idea is that the entire denominator gets multiplied by those values, which would lead to this distributing in. So we have these two terms in here because of that addition. We have the 1 and the sine squared over cosine squared, and both of them are going to be multiplied by sine squared and cosine squared. So what that means is, just to kind of simplify this, I'm just going to write that so it's a bit closer, is that the sine squared over cosine squared gets multiplied, but so does the 1. So absolutely every term that's in your complex number gets multiplied. So up here, we did this multiplication so that sine squared would cancel out. So up in the numerator, all we're going to have left over is cosine squared. Now in the denominator, we're going to have this 1 times sine squared cosine squared. And plus, and over here, those cosine squareds are going to cancel out with each other. So we're going to have sine to the power of the fourth power. All right, so the steps were plug in sine and cosine, get rid of those complex numbers so that we have a simpler rational expression to work with. And now I need to look at this and think about what I can do. And actually, let me quickly say what we cannot do, because you might be inclined to cancel out those cosine squared values. We cannot do that. Because of that addition symbol right there, this entire expression in the denominator is stuck together. So we can't separate that. However, what I could notice, and again, if it helps, we could think of this as like y squared over x squared, y squared plus x to the fourth. It's kind of like the equivalent. What we have in the denominator is a common factor. This x squared or sine squared is a common factor. So I want to factor out sine squared. I want to see where that takes me. Some of this with verifying identities is just kind of seeing where it takes you. Have an eraser ready. You might have to go backwards and kind of start over. That's kind of part of the process with these. So cosine squared, and I'm going to factor out sine squared. So what that will leave me with is for the first term, I'll have cosine squared. And then plus, since I had sine to the fourth, I've factored out 2 of those, so I have 2 left. So there's my denominator. Now, cosine squared plus sine squared is making me think about the Pythagorean identity. We know that sine squared plus cosine squared is equal to 1. So, and cosine squared plus sine squared is the same thing. So all of that is just going to turn into a 1. So really all we have is cosine squared over sine squared, which cosine over sine is cotangent. So we end up with cotangent squared. And that's it. We ended up where we wanted to be. So what's nice about these is also having in mind where you want to end up, because while this is a simplified form, it's not quite in the form that we want to get to. So substitute in sine and cosine, eliminate those complex numbers in there, and then with that, it's just looking for what are the possible things we can do, and it might require some factoring like we did there, and then using the Pythagorean identity to simplify. All right, here we have cosine squared over 1 minus sine, and we want that to equal 1 plus sine. So cosine squared t over 1 minus t. Let me go ahead. Sometimes I just like to write it down again to help me out, especially if I'm going to use some operations. Now looking at this and thinking about what can I possibly do, it can feel very stuck. And there's not much to do. There's no changing to sine and cosine because it already is there. There are no rational expressions to combine. There's nothing to factor. It's very stuck. So where my mind goes is that up here, I'm seeing cosine squared. So what I'm going to do is play around with the Pythagorean identity, because in the Pythagorean identity is cosine squared. So I'm going to see what I can do in terms of making a substitution for cosine squared. So if I take my Pythagorean identity and isolate cosine squared, that's equal to 1 minus sine squared. So let's go ahead and make that substitution. So this is 1 minus sine squared over 1 minus sine. Now, 1 minus sine squared, and if it helps to see it in this form, is the same thing as like 1 minus x squared. And we can factor that. This is the difference of squares. So factoring that, what it would look like is 1 plus x, 1 minus x. So I'm going to do the same thing, just with sine. So we'd have a factor of 1 plus sine, 1 minus sine, all over 1 minus sine. Again, that subtraction, I'm just going to draw parentheses down here because it groups it together. And now I can make a cancellation because I see that entire expression of 1 minus sine and that entire expression of 1 minus sine. So those cancel out, and all we'll have left over is 1 plus sine. And we're done. So keep in mind all of that factoring that we've done previously in math, and just think about applying it to these trig functions. All right, with this one. So we're definitely going to start over here because trying to simplify that one would be way too difficult. Something we could do is we could start foiling. However, that's going to get messy pretty quickly. And I'll be honest, when I was making the answer key, I went that route. And so that's that case of just have an eraser ready because you can try it out. And then if you start to get a headache, kind of go back to the beginning and see if there's another way to go. So instead of foiling and like multiplying, having like secant squared and tangent squared and secant times tangent in there, what I'm going to do is I'm just going to start by that step of substituting in sine and cosine. And what I found with this kind of trial and error here is that just having sine and cosine will make things simpler, because then these two pieces will relate to each other. So changing to sine and cosine, So secant is 1 over cosine of b plus, and then tangent is sine over cosine. And then times secant 1 over cosine minus tangent, which is sine over cosine. Now what we have here are common denominators within those parentheses, so we can just combine these. So we can add them together, so 1 plus sine of b all over cosine times 1 minus sine all over cosine. And now we can multiply these together. So multiplying the numerators, we'll have 1 plus sine of b over 1 minus sine of b all over cosine times cosine, so cosine squared. Foiling, we'll have 1 times 1. That like negative sine of b, positive sine of b, those will turn into a 0, but then you'll have minus sine of b squared. So foiling that out, you'll end up with 1 minus sine of b squared all over cosine squared. I'm seeing lots of things to do with the Pythagorean identity here. I'm going to look at that 1 minus sine squared of b, which, if we have our Pythagorean identity and I make 1 minus sine squared, that's the same thing as cosine squared. So cosine squared, over cosine squared is going to give us 1. There we go. So substitute sine and cosine in, combine your rational expressions, multiply through, and then just simplifying down and looking for that Pythagorean identity when you can. All right, 2 more here. So with this first one, so everything's in terms of sine and cosine. So with that, I'm not going to make any substitutions in there. However, this gets pretty stuck because these are different variables. It's like I have 3x squared plus 4y squared. I would think about factoring out if I could, but there's nothing common to factor out. So this gets really stuck. So seeing sine squared and cosine squared, I'm going to think about the Pythagorean identity and seeing what that can offer me. So again, sine squared plus cosine squared equals 1. I write it out every time. You don't need to, but I do it just because it can be, there's a common mistake made of like moving things around incorrectly and making the incorrect substitution. So I just go slowly with this one and making sure that it is in fact like 1 minus sine squared and not 1 plus sine squared or something like that. Okay, so figuring out what I want to do with the Pythagorean identity, what I'm going to look at is that my final answer is only in terms of cosine squared. So what that makes me think of is I want to make a substitution for sine squared. I want to put that in terms of cosine squared. So I'm going to do is solve for sine squared, which would be subtracting cosine from each side. So I can make this substitution of 1 minus cosine squared. So we'd have 3 times 1 minus cosine squared in parentheses plus 4 times cosine squared. I'm going to distribute the 3 in. So we'll have 3 minus 3 times cosine squared plus 4 times cosine squared, which that right there is the equivalent of like 3 minus 3y squared plus 4y squared. So now we have these like terms that we can combine with each other, and it'll come down to a 4 minus 3, which is a positive 1. So we'll have 3 plus 1 cosine squared. And that's where we wanted to end up. It's all good to go. All right, last one here, sine squared b minus tangent squared b. All right, let's make substitution in terms of sine and cosine. So sine squared is going to stay the same. minus tangent squared, which is sine over cosine. I want to combine these into a single term. So with that, I need a common denominator. So where I have the sine squared over 1, I need a denominator of cosine squared. And whatever I do to the denominator, I also need to do to the numerator. So this will be sine squared times cosine squared over cosine squared. Let's go ahead, we can go ahead and combine them. Minus sine squared all over cosine squared. All right, in that numerator there, I have a common factor of sine squared, so I'm going to go ahead and get that out of there. So I'm going to factor out sine squared, and that'll leave me with cosine squared minus 1 all over cosine squared. So what I can notice right here is that sine squared over cosine squared, there's my tangent squared, so that's working great. My issue is this piece, the cosine squared minus 1, which again, with cosine squared and 1, that's making me think the Pythagorean identity. So I'm going to play around with the Pythagorean identity and see if I could get this cosine squared minus 1 scenario. So here's my cosine squared. I don't want to subtract it from both sides because that would give me 1 minus cosine squared, which is different. But if I subtract 1 from both sides, so I get my positive cosine squared minus 1 equals 0, then what I could do is to get that all alone, I would subtract sine squared from both sides. So what that would give me is that cosine squared minus 1 is equal to a negative sine squared. So with that, I can make the substitution of negative sine squared. Oh, in fact, I'm going to go ahead and get that tangent squared in there. Sine squared over cosine squared would turn into tangent. That cosine squared b minus 1 is a negative sine squared b. So there we have this tangent squared times a negative 1, so that negative could come out front. And there's sine squared. And that would be done. Alternatively, another way you could go about this is when you're at this cosine squared b minus 1 over cosine squared, you could factor out a negative 1 there, so making it negative sine squared b times 1 minus cosine squared. So it'd make the negative 1 positive and positive cosine negative cosine. And then you would just have your direct substitution of sine. That would work as well. That's where there could be more than one route with these. All right, so all of that to say, these are some identities. Every case is going to be different. You'll have a different route to go. It's just taking the time to practice and kind of training your brain of what to look for. So my typical routine is start with changing everything to sine and cosine, simplify down. If there are separate rational expressions, combine them together, and just through the process, kind of keep looking for the Pythagorean identity, and also always think about what your end goal is, where you want to end up, because that can kind of help you with the path as well. But these won't always be a perfect process. You might have to try something and just realize like, okay, I can get there, but this seems really intense. Maybe I should go back and have gone a different route. That can happen with these, and just kind of embrace it and go for it and try them out. And yeah, so this is the idea of verifying trigonometric identities.